Hello folks, today we're going to talk about modeling situations with exponential functions. So let's take a look at this problem. We are saying that we're going to open a savings account with an interest rate of 2.35%, which I'm going to go ahead and write as 0.0235 for my interest rate R. And we have an initial investment of $350, and we want to know how much would be compounded. How much would you earn in your account after 10 years if you compounded at these different rates? So yearly, so once per year, or quarterly, which is 4 times per year, or monthly, so 12 times per year, or weekly, 52 times per year, or daily, 365 times per year. So those are going to be our different n values that we are looking for. So let's go ahead and write an equation here to model this situation. And I am going to say that A of n, so the amount of money I have with respect to the number of compoundings, is going to be my initial deposit of $350 times 1 plus my rate, which is 0.0235, divided by n, which is the number of compoundings. I'm going to raise that to n, the number of compoundings, times t, the time, which is 10 years. So I'm going to write that as 10 times n. So this equation right here is going to tell us an easy way to figure out how much is earned with each different value of n, so each different number of times compounded. Because remember, these are the values we're looking for. So we are going to graph this function, and we are going to plug in all those different values. So let's go ahead and enter this into our calculator. When you type this into your calculator, I would recommend you go 350, then open a parenthesis, 1 plus 0.0235 divided by x, close your parenthesis, caret, and then I would do parenthesis, 10x, parenthesis. And go ahead and graph that, and let's think about what these questions imply here. So what does x represent in this equation? Well, x represents n, the number of compoundings. If you jump back to what we wrote on the other page, this is the same exact thing except with x substituted in for n, because we're entering it into our calculator, and so we have to put it in terms of x. And now the question is, how can we find a good window for this function? So we want to remember that our x values are representing the number of compoundings, and we're looking at all those different values up to 365 times per year. And so I'm going to put my x min at 0, and I'm going to put my x max at 365. And then at that point, I'm going to hit zoom option 0 to do a zoom fit, and that should give me a pretty good window to start with. And now it says, what does the horizontal asymptote of this function represent? Well, remember, we are graphing the different amounts earned over 10 years depending on the number of times compounded per year. And the horizontal asymptote is, if you think about it, the limit as x approaches infinity, and it's going to level out to some value. And the value is representing what happens to this function as you let the number of compoundings go to infinity. So what happens if you are continuously compounding interest? So when you graph it, you're going to get something that looks like this, depending on how you set that window up. The blue graph there is our function, and then we can see that as x increases, it levels off to some value, whatever the value of that red line is. And we wanted to find all those different numbers depending on the number of times we compounded per year. So hit trace and then type in 1 and hit enter, and you'll get your value for yearly. Then type in 4 and hit enter to get your value for quarterly, etc., for each of those values of n. And you should find the values I'm about to show you. So you should get those values. Notice that as you continue to increase the number of times that we compound the interest, the amount that you increase each time is not all that much more. And that's what the shape of that graph is telling us, because it is leveling off to that asymptote. But the question is, what is the value of that asymptote? Which is basically asking what is the limit as n goes to infinity, as the number of compoundings goes to infinity. Well, we already talked about it in some previous videos here. If you take that limit and let the number of compoundings run off towards infinity, you get the equation for continuously compounding interest, which uses the natural number e. And so the equation of that red line would be 350 times e to our rate, 0.0235, times the number of years, 10. So we do actually know the value of that horizontal asymptote. And so you will see the equation for continuously compounding interest listed as A of t equals P, the initial principal amount of money, times E, the natural number, raised to the rate, the yearly interest rate, times time. But this is also the same equation that can model population growth. So that P can stand for the starting amount of money, or it can stand for the starting population. E is always just the natural number, and R could be an interest rate or a growth rate or a rate of decay, depending on the situation. Can still all be modeled with the same equation, and then T will always be time. And I remember this as the PERT equation because of the shampoo PERT plus, but you were taught this last year as the poked equation, but they represent the exact same thing. They're going to take the initial population and multiply it by e raised to the power of whatever the rate is, multiplied by the time. So poked or PERT doesn't make a single difference. But that's what we want to do to get it today. We want to model continuously changing populations using the poked equation or using the PERT equation, depending on how you want to remember it. And we want to use these to help us solve and write exponential equations. And so let's go ahead and look at this first situation. We have a culture of bacteria growing continuously in a petri dish at an exponential rate. The initial number of bacteria, so our P naught there, let's write P naught, is our initial population is 200, and then after 7 days it increased to 500. So I'm going to say that A of t, I'm kind of combining my two equations here, A of t, which is going to be the population after t days, A of t, so I can say that A of 7 is 500, A of 7 being the population after 7 days. And I need to figure out what my rate is, but I can write the equation 500 equals 200 times e to the r times 7, because I'm saying that after 7 days, my population will be 500, given a starting population of 200 and some rate r. We don't know the rate, we need to find it. And we have not yet explored algebraic ways to do this, so what I'm going to do is I'm going to graph this on my calculator. I'm going to say that y1 equals 200 times e to the power of x times 7, and I'm going to say y2 equals 500, and I'm going to find the intersection point to find the value of r, aka my rate. So when you graph this, we're going to need to find a good window for it. So things we know that r, our rate of growth, is going to be a positive number because our population is increasing from 200 to 500 after 7 days. So when I make my window, I am going to go from 0 to 1 for x, and that's because I know it is a positive rate, and it's going to be some decimal. And then for y, I know that I'm looking for the intersection at the y value of 500. So I'm going to graph 450 up to 550 for y, and do that, and you should get a graph that looks kind of something like this. And we're going to calculate that intersection point, and it's going to tell us that x is equal to 1.131. And now let's go ahead and write our equation. So we're going to say that a of t is equal to our initial population, 200, times e to the power of 0.131 times t. So this says the population follows this model after t days, because our units are days here. And so we want to know what is the size of the population after 10 days. So we want a of 10, which is 200 times e to the 1.31. See what I did there? Now evaluate that on your calculator to find that the population is roughly 741. So then the problem I want you to do for homework is as follows. The amount of a 20 milligram dose of a medicinal drug remaining in the bloodstream falls continuously at an exponential rate. And so after 2 hours, we know that 17 milligrams remain in the bloodstream. And to the nearest half hour, how much time is required for at least half of the original drug dose to leave the bloodstream? So we want to answer this question. It's going to be very similar to the last problem, but how are we going to find the rate that the drug leaves your body? Well, let's write an equation and think about what we know. We know that after 2 hours, 17 milligrams remains in the bloodstream. So A of 2 equals 17. And so we're going to write the equation A of t equals the initial size, which is 20. The initial amount of medication is 20 milligrams, times e to the power of our rate, whatever that happens to be, times time, which is being measured in hours. And so we're going to plug this in. We're going to get 17 equals 20 times e to the power of r times 2. And so we're going to do just like we did in the last problem. We are going to graph y1 as 20 times e to the 2r. I'm going to graph y2 as 17. And now recognize this time that the amount after time t is going down now. As you increase time, you have less and less in your body. And so this time the rate is going to be a negative number. So for x, I'm now going to go from -1 as my minimum up to 0 as my maximum, because it's going to be a negative rate. And then y values, again, acknowledge that we are looking at the value of 17 there for an intersection point. So I am just going to go 15 to 20 for my y window, and let's see what this looks like. It's nice to think about what window makes sense before you graph it, because then we get to see what we want to see pretty much no matter what. So when you graph these two functions, we're going to get something that looks like that, with a line intersecting it about there. And that purple line is the only bit of axis that we see, because think about our window, -1 to 0, and then 15 to 20. So we don't see that x-axis there. But we do find that intersection point, and we calculate it to get x equals -0.081. And you should either round that right there, or you should store that variable. That would be the preferable option. But regardless, we found our rate. And now the question is not actually asking us for the rate. We want to know that how long does it take for half of that dose of medication to leave your body. And so now that we've found our rate, we are going to write our equation. A of x equals 20. And I'm not even going to say A of x. I'm going to say, go ahead and write it as y1 equals, because we are entering this into our calculator, 20 times e to the power of the rate we just found, which was -0.081, -0.081 times x. And now here x is representing the time. And so we want to graph this, and we want to graph another line though, y2, because we want to know how long it takes for us to get a y value of 10 to represent that half of it has left the bloodstream. And so let's think about a window now. Remember that it took 2 hours for 17 milligrams to leave the body, and we're looking to get to 10. So I'm just going to try something here, see how it looks for us. I'm going to go for my x min to max. I am going to go 0 up to 10. We'll see what it looks like. And then for my y values, I'm going to go 0 up to 15. And let's see how this looks. So when you graph it, it should look something like that, and you can calculate that intersection point right there, which you'll find to be x equals 8.557. And remember what x represents. X is time, so really that is our t value, the hours, until half of it is gone. And so it's important to read the question here, because the question says, to the nearest half hour, how much time is required for at least half of the original drug dose to leave the bloodstream? And looking at this and reading that it said nearest half hour, you're probably tempted to say the nearest half hour is 8.5 hours. But that would be incorrect, because the question says we need at least half of the dose to be out of the bloodstream by the time we give our answer. And at that point, if we are at an x value ahead of 8.557, that means we are technically somewhere about there, and that is above that line, meaning that we still have more than half in our body at that time. So we would have to answer this as 9 hours. 9 hours. That would be when we could confidently say that there's less than half of the medicine currently in our bloodstream.